I'd like to welcome everybody to the 2024 Stephen H. Davis Lecture. To those on Zoom, there's a question and answer button. Please feel free to send your questions anytime during the lecture, and they'll be answered afterwards. We'll go through them. Okay. This is the fifth Stephen H. Davis Lecture. The first one was in 2019, and the lecture was established to honor all of the many contributions of Steve Davis, the fluid mechanics, material science, applied mathematics. Steve attended that, and if you were there, you know that he was extremely happy. The next one in 2020 was canceled because of COVID. 2021, we had the meeting, Steve got ill and unfortunately passed shortly after the meeting. Since then, it has been annual. Anyone wanting to know about the life and work of Steve, if you go to the ESAM department's webpage under SHD lecture, there are some reviews about his life and some of his research. Okay. So we are fortunate today to have as our lecturer my assistant here, Kate Stebe. Okay. To tell you a little bit about Kate, she is the Goodwin Professor in the School of Engineering and Applied Sciences at the University of Pennsylvania. She's in the Department of Chemical and Biomolecular Engineering, slightly different than here, okay? She is, to tell you a little bit about her academic career, not a lot, you can read about it, okay, on our webpage. But I can tell you she started her academic career at Johns Hopkins. And it's interesting that Steve Davis started his academic career in the US at Johns Hopkins also. So there is that connection outside of the connection in work, okay? She moved to the University of Pennsylvania where she was deputy dean and she served as a deputy dean and a chair of the Department of Chemical and Biomolecular Engineering. She's a member of the National Academy of Engineering, the American Academy of Arts and Sciences. She's a fellow of the American Physical Society, and not giving you the full list. There's quite many other honors, okay? I'm happy to have her today. I think she well represents Steve and his work. And the title of her talk is Swimming in Pneumatic Liquid Crystals. So yours.
Thank you. Let me try to put this back now. Also need Steve to hold it for me all through my talk. Okay, great. So I'm really honored to give this lecture. Steve Davis was a foundational researcher, but he was also such a genuinely kind person. And you mentioned that I started at Hopkins, and he and Paul Neitzel and others who were in the mechanics group at Hopkins, like almost get like rhapsodic at talking about like how great it was to gather together for coffee and discuss phenomena and define problems and identify a problem that could have impact. And just a really, really lovely person. And I'm really glad that the lectureship was started while he was still alive so that he got to have that Huck Finn experience of hearing everyone sing his praises while he was there. I just wanted to just give an example of a piece of work by Steve. It's worked with, I believe, did he direct her PhD? Liz Dussan's?
Yes.
Yeah, so Liz Dussan was if you're a feminist in chemical engineering, she's a hero. She worked on these moving contact line problems with Steve. I know that she wasn't always made welcome and that Steve made a point of treating her and her penchant for intellectual rigor with tremendous respect. And the problem that they defined was to look at three-phase contact lines. And if you read the paper, it is dense and scholarly, and it's filled with detailed kinematics. But it also had incredibly beautiful, simple to understand experiments in which they put droplets of liquid dye on a rolling drop and demonstrated that the drop advanced with a tread-like motion. So that schematic is reproduced here by in a textbook or a review article that became a foundation of a textbook by Dijen. So it's one of those problems that, done properly, ripped across the world. And it's also an example of something foundational where we still don't always know what we're doing. So this is a problem about recent work on contact lines. This is done by Vinny Manoharan at Princeton, which shows that a droplet particle held under a fluid interface, that when it attaches to the fluid interface, there's this rapid evolution of kinetic energy as popping onto the interface gets dissipated. That was known before they did the work. Then there's this extremely slow tendency to reach equilibrium, indicating that contact lines can remain pinned and out of equilibrium. And they quantified the area per defect on the order of nanometers, the energy per defect from 1 to 10 kT, that the surface pinning sites, topographical features on the particles, and that I'm saying because I want Mike Mixis to work on this problem. I did some work on it. It's thinking about a particle that's trapped at a fluid interface and the distortion it makes around it. And if you decompose that distortion around the particle in Fourier modes, the 0th mode is the monopole. It's just a circle. And that means that you'd have to be heavy or light to distort the interface. And then the next, and if you have no external force, you're stuck in the plane of the interface. So if you're tiny and your bond number is small, you're pretty much in the plane of the interface. The dipole, unless you had an external torque, will get rotated out by surface tension. So the first surviving mode is the quadrupolar mode. If you place particles like that, here, I'm going to try to move this screen over to there, like that on I have a little blank spot there. Imagine I didn't have a blank spot in the upper right-hand corner. There's a particle that's hovering above a curved interface, and that interface is curved using a micropost. And everywhere on that interface, it's an approximation of a monopole. The surface is a saddle seat. When the particle attaches to the interface, its distortion reads the underlying curvature field. So this is just a movie of spheres that have attached to an oil-water interface and are migrating uphill to minimize the capillary energy. And here's what happens if you have lots of them. So you see sort of particles that are not translating. Those are falling oil, hexadecane, and attaching to the interface. But look at the quadrupolar symmetries to the structures that are emerging. So there are interesting open issues in this problem, and I wanted to bring it to Mike's attention, so I used this introduction. But I also wanted to bring it to all of your attention. You look at a problem, you say three-phase contact lines. We understand those. We don't. And then different ones are different. And in different settings, they're different. And science is special. And if we understand what makes different settings special, there are new opportunities to use the phenomena. And I think Steve was on to that. So that's my lengthy introduction. I won't be talking about this further. Mike will present a paper in a year or so. Okay. So what I wanted to talk to you about today is this problem I've been working on, where I've been looking at colloidal particles that are placed in nematic liquid crystals. And so this four-arm structure, I'll tell you more about it in a little while, but it's made of SU8 epoxy resin and it's sputtered with nickel. And it's in 5Cb, a simple nematic liquid crystal. And if I rotate that thing with an extra, and you can see these little, that woman keeps interrupting me. It's me. Okay, you see there's glass beads that are nested. As we rotate this object, things happen. And I'll tell you more about those things. That object that's licking is some form of a topological defect. And I wanted to understand what it was doing. So I'm going to meander through sort of what motivated us to look at such a thing, and then how we've been thinking about what are the special opportunities nematic liquid crystals offer when we push them far from equilibrium. Okay, so this is just an introduction slide, and it's just a way to think about nematic liquid crystals. And in fact, last time I spoke here, I used this slide. I promise the talk will be different in like 3 slides. Okay, so let's imagine we had elongated molecules, and we think about them as molecular grains of rice. And if you have dry rice in a pan and you shake it, that the rice will co-align. and it's maximizing its translational entropy by giving up its orientational entropy. The temperature does that for the molecules. It's shaking them, and they prefer to co-orient because of their shapes to maximize their degrees of freedom. So since their minimum free energy state is to be co-aligned, not being co-aligned costs free energy. And so we can force in distortions by using colloidal particles. If I, for example, place a sphere in a nematic liquid crystal, and I give it boundary conditions, for example, there are known chemistries that we can use to, I have no point, I'll just come here. So if I put, I can treat boundaries with chemistries. For example, self-assembled monolayers of surfactants will tell the molecules all to be perpendicular to the surface. A rubbing, actually, everyone has a favorite velvet cloth from a particular vendor in Japan. I'm not kidding. And you gently rub a boundary, a polymer boundary, and then the nematogens will lie planar to the interface with anchoring energy. So we can define the orientation of the molecules at the interface. And if we do that, for example, on a spherical colloid, that we get a distortion that would decay with distance from the colloid and die out in the far field. You would also get what we would call a topological defect. Here I show it as this little red dot. It's a required zone of disorder that emerges in the liquid crystal. Yeah, it's fine. I have a digital one. There's a little zone of disorder that emerges in the liquid crystal that's topologically required to fit that spherical distortion, a +1 defect in a uniform far field nematic. So you can get these zones of disorder that emerge. And while they might have some internal structure, they're zones of highly reduced order. And they scatter light. So here under an optical microscope on a 10 micron diameter bead, we can see it. Right, so it's nanometric, it's a couple of molecular length scales, but because they scatter light, we can see them in an optical microscope. And if I have many particles, that they can interact because the distortion field seen by a neighboring particle will minimize the free energy. If I can see my neighbor, I can attract to my neighbor and reduce the distortion in the domain, and thereby start to form assemblies that are driven by these far field distortions. So this distortion, for example, is called a dipolar distortion. The colloid's a +1 defect. Its companion defect is a -1 defect. So just like an electrostatic dipole, it's called a dipole. And in the far field, like an electrostatic dipole, it will form chains. It will attract, and in the near field will chain up. The colloid can also form what's called a quadrupolar distortion, which is also aptly named a Saturn ring. And that Saturn ring distortion has top-down symmetry. It attracts, it's not as long range, it's distortion, and it attracts to form structures with zigzag symmetries. So all this was long known before I got started. And when we got interested in thinking about playing was we said, what if we put a planar boundary right under that particle? And actually, that was already in the literature. Oleg Droventovich did that experiment. And there we'd have truncated the range of decay of the distortion. And so the distortion would hate it. And it would rise up to minimize its free energy. So typically, these particles are repelled from planar walls that force them to truncate their natural range of decay. So we wanted to play with that. So could we mold boundaries that were attractive instead of repulsive? And so we were inspired by some lock and key ideas. And so what we did was we made a wavy wall. And the wavy wall would be a source of bend and splay in the domain. So bend, twist, and splay are the fundamental distortions. And here we're forcing in bend and splay. And the bend and splay from the wall was complementary to that from the particle. So if the particle nested in that site, then the likes, which we say that all the time in chemistry. Okay, but here it's distortion likes distortion, similar distortions overlapping, get rid of distorted volume and minimize the free energy. So we just started using, this is where we began our game of using SU8 epoxy resin just to make things, make shapes that we could treat and force in boundary conditions that would be interesting boundary conditions. So this is an SU8 epoxy resin wavy wall, and we're going to treat it with the chemistries to tell the molecules to be perpendicular, sandwich it between glass plates, and those glass plates were treated to make the surface oriented planar. Okay, and so we forced the wall to have this homeotropic anchoring and that distortion. Okay, and so here's just a movie of what happens. This is this like a 10 micron radius glass bead adjacent to the wavy wall, and it's minimizing its free energy. We just put it into the nematic phase, and she's ladylike. She's curtsying. She finds her free energy state. And so you can play games with the relative curvature of the wall and the colloid. You can calculate, you can use a Landau-Dijen formulation to calculate the director field and move the colloid about relative to the wall, et cetera. And so we played lots of games with this anchoring. I'm so sorry, we have a blank spot. And so that was the work of Yiming Lo, Francesca Serra, and Giuseppe Boniello. But it also got us started thinking. Next student on the project was Tianyi Yao, and he said, you know, we've already shown that we can get colloids to come to the boundary. Wouldn't it be interesting if we were to make some wavy object that could move to different locations and that could interact more freely in space? And so we made our four-armed monster. So the four-armed monster is made of SU8 epoxy resin. It's treated with nickel, treated with the surfactant that tells it to have homeotropic anchoring, perpendicular anchoring, and then removed from the substrate. So its poor little bottom never got to see the surfactant, and it has hybrid anchoring, therefore, planar anchoring on the base. And we thought, well, okay, fine. And later we find out that this would rule our lives for the next 3 years. Okay, so we're making some three-dimensional director field that has something special. Okay, but what we started to do was really, we said, you know, if we look at the director field here, just solving for it, I'll tell you more about it in the Landau-Dijen formulation, we could see that we see regions of bend and sway coming from each of the curved regions where a colloid could dock, and hiding under our arrow, because we didn't really understand it well yet. You can see it. You can see my little arrow. Hiding under there is a red dot. So that's what that simulation gave us as the companion defect. And we really didn't understand it. And we started, we said, we're going to have to do some defect management. That's what we called it. Like, oh, that thing. Okay. And so I'll tell you more about it as we go. So that's Chen Yi, and he rotated the four-armed monster. So here it is. The colloid is in this external magnetic field, and it's being rotated about an axis perpendicular to cell. So cells like this, and it's being rotated in plane. And you see that companion defect. It's doing some sort of sweeping and hopping motion. And we watched it many times before we said to each other, it's moving from the left side of the screen to the right side of the screen in a purely rotational field that's applied perpendicular to the object. And Tianyi said, you know, I want to graduate. So the object, the four-armed object is about 25 or 35 microns thick, and then about 15 to 20 microns above. So the sandwich and the sandwich thickness itself is about 45 microns or so. And so that the thing can't tilt fully. So it's a little bit confined, but it's not very tightly confined. And confinement does play a role, which I may or may not get to. Okay. We tried to understand it, but we really, I don't know, Tianyi did graduate. He wrote a very nice paper. But we realized when he was done that we still really didn't fundamentally understand what are the rules for swimming. We had a lot of ideas, but to probe into this question. So Miha Ravnik and his, I think then postdoc and now independent researcher in Ljubljana, and I took this on saying, can we start to understand how does one swim in a nematic liquid crystal? And we retreated to spheres. So I gave up the four-armed object to start and just ask yourself, what does a sphere do? And so if we look at a sphere and we thought about a sphere, here's the cell, we're going to rotate about this axis. And so it's a purely rotational motion, no rolling. In a Newtonian fluid, this should be very boring. And so, here's this might actually be isotropic 5Cb, but we rotate this nickel-coated glass sphere and it diffuses, but it doesn't translate. So you notice that it has a bump on it. This was Mojtaba Rajabi's experiment. And I said, Mojtaba, that sphere looks weird. It has a thing on it. He said, yeah, that's really fortuitous. This is Mojtaba, everything. And it's true. Once you hear his logic, it's really fortuitous because you can see that our plane is in field, that our field is in plane, that we don't have rolling motion, that's a marker on the sphere that lets us. So we like Pinocchio. Okay. So in the Reynolds number, in a Newtonian fluid, we expect this to do nothing interesting. But nematic liquid crystals are special in that they're highly non-Newtonian in very special ways, that they've formed spontaneously these companion defects, which you can configure, et cetera. And so for this experiment, the relaxation time for viscous to elastic effects in the system, where K would be the energetic cost to bend, twist, and splay, and gamma 1 is the rotational viscosity for the nematogen. The relaxation time scale is about 1 second, and it's not hard to challenge that for rotational frequencies at which we would have tiny Reynolds numbers. And in fact, for 5Cb, a very common nematogen, which I'll be using every experiment unless I say otherwise, that the Erickson number then is about 10 to the 5th times the Reynolds number. So you can have very interesting dynamic effects, even at extremely slow motions in these systems. And the free energy functional that describes the response to distortion is highly nonlinear. And so you can expect really interesting responses. So here's Mojtaba. Oh, he's hidden. There he is. It's not fortuitous this time. This was his question when he came and joined us. He said, well, this equilibrium structure for this dipole, it already lacks 4F symmetry, but it's at equilibrium. But he said, it seems to me, and he's a very intuitive person, he said, it seems to me if I rotate it, that I could distort that for F symmetry. And for example, if I were to do a rotation, you can think of the defect as an object which can be dragged. And could it be dragged off of the North Pole? And if it were, then recognize the entire director field around it is also distorted. That's setting off a far field distortion. And that could break right-left symmetry. And we were trying to be careful that these were not all roughness effects. So that's just some AFM of looking at the sphere and saying that it's a smooth sphere. Okay, so here is the experiment. We have nickel-coated glass spheres. And I said, well, you know, it's a little funny because we have big ones and we have little ones. And he said, yeah, it's great. It's also dipole up and dipole down. And we get them with 50-50, it's random. They always form at equilibrium with their companion defect, either at the North Pole or the South Pole, aligned with the far field defect. But he rotated them and recognized the larger one is also more confined. And you can see that the dipole is a little bit tilted and they're moving jauntily along. And so what makes this interesting is that topological defect is formed spontaneously in the fluid. So our colloid is completely, it has no broken symmetry. And the forcing of fluid has no broken symmetry. And so the broken symmetry is emerging spontaneously from the fluid itself. And so just so that we can see that the larger object had the beta, we'll call the tilt angle of the defect, had the greater tilt angle, and it had the faster translational velocity. And we could do lots of experiments to look at the swimming speed, the tilt angle, and the swim speed direction. And the swim speed direction in particular is usually almost perpendicular to the far field director. So if our far field director is like this, we usually go just in the X direction. There's some weak Y component, but it's very weak. Okay. And we're still having a discussion as to whether or not this is linear in the Ericsson number. It is indeed linear here for Ericsson numbers above, let's say, around 0.04. And down here, we're having an honest discussion doing particle tracking to tease out whether we have drift, migration, or diffusion, et cetera. So this suggests, at least, that the defect angle and the swim speed are linear in the Ericsson number. So Nematic is a doctoral student in Slovenia who's working with Žiga, and he's been working on the analysis for this problem. And so the first piece was to think about the defect as an object and to treat it as something that has drag because of the rotational flow pulling on it, and that some elastic restoring force because the director field would like to return to the North Pole. And so to think about the drag, that would be some drag coefficient times the velocity. And the drag coefficient is typically ascribed that the rotational viscosity is considered the most important. And in work by Stark, that this is sort of a drag coefficient that's been discussed for on the defect itself. And next is to derive the elastic force. And that's going to come from the free energy functional, saying that some derivative of the free energy with respect to the angle would allow us to get to the elastic force. And so they're posing this ansatz first of saying to do analysis, they typically have to assume a weak dipole, which does not really correspond to experiment, and then calculate the distortion of the liquid crystal. And here they're using a equal cost to bend, twist, and split, so they get a relatively simple free energy functional and an anchoring energy. And taking, and so this is the free energy functional they get, and then differentiating that with respect to beta, they can get an elastic force. Equating those two gives us an argument that relates the material parameters of the liquid crystal to the Ericsson number and the beta. And so we can expect that the beta is first order in the rotational frequency. It depends upon the radius linearly. So larger is the colloid, the bigger the distortion. And then placing that to tease the Ericsson number out, which is typically this relaxation time to the forcing frequency, we can have prefactors that include anchoring energy, the bulk elasticity, and geometry. Okay, so that's predicting that we should see beta being linear in ER. And here for parameters that correspond to our experiment, it's not doing a bad job capturing the experimental trends. Next, and this is work that I was discussing this morning at 7 a.m. with Žiga and Ene, who finished this on Sunday. So it is hot off the presses, is trying to think about, could we use a reciprocal theorem formulation to start to understand how this flow field is generating translation. And so the idea was to look at the Leslie-Erickson stress tensor that describes the stresses in a liquid crystal. There's an elastic energy cost and a viscous energy cost. And the sum of these two give the Leslie-Erickson stresses. And in liquid crystals, there's a zoo of different viscosities. So there are viscosities to different forms. Here's one that's to a certain rotation. Here, alpha 4, this is the analog to just a Newtonian viscosity. But the others are seeing different components of the nematic liquid crystal and the distortion that's occurring in the system. And D would be the rate of strain tensor, and N is a vorticity tensor. And so, this is the underlying Leslie-Erickson stress tensor, which can be written down as the total stress tensor as some Newtonian-like part, which is coming from this piece, pressure-like part, and then everything else. So sigma here is everything else. This sigma has to be constructed by coming in and looking at a first order perturbation with respect to this tilted dipole to find the contribution of each one of these viscosities. The alpha 4, which is the Newtonian piece, is taken care of. That's appearing here. And everything else is being calculated for that rotated dipole ansatz. And then we need to use, to set up a reciprocal theorem, we need to have the flow of interest, which is our problem, and the auxiliary problem, which here we're just taking a sphere that's moving steadily under Stokes' flow. And so our problem is force-free, meaning there's no external force that's being applied. And the auxiliary problem is free. And that allows us to take our reciprocal theorem and write it this way, that the terminal velocity of our particle, that's what we're after, is related by the force here that's on the particle in our auxiliary problem. Our stress tensor, which was calculated for the rotated dipolar ansatz, and this the velocity field that goes with our auxiliary problem. So they go about evaluating that and find an expression for the x and y directed velocity. It allows them now to say what can they predict using this approach about the velocity of the surface of the terminal velocity of the sphere itself. And so looking at the arctan of the y and x direction lets them predict the swim direction. And prediction is doing a pretty good job with respect to experiment. The black line is the prediction. And how strong would x-directed velocity be, for example, for 5CB, is capturing the low Ericsson number data pretty well. So this is saying that, you know, the excitement is that the fluid itself is generating this defect that generates this broken symmetry under rotation. And then I guess the excitement here is that the machinery of fluid mechanics can rationalize what we're seeing and let us see that this concept of weakly offset dipole is consistent with the motion that we're seeing. They also predict some nice dependencies on the material parameters. And there's this known phenomenon, and I think it comes down to Jeffrey orbits. There's this known phenomenon for liquid crystal molecules that as they get longer, if you have, for example, 5CB, the molecule that I've done all my work on up to now, in shear flow, it's known that the nematogens should be able to attain a stable orientation in a shear flow. But if they get longer, they undergo what's called flow tumbling, and that they won't come to a nice equilibrium alignment. I'm not imposing a shear flow, but that concept of flow tumbling is a nice way to group different molecules. Are you flow tumbling or not? And so this mixture of 8CB and 7CB is a flow tumbling nematic. And it's fluid at room temperature, which is why we studied it. And here's our little rotator, and he just cut free. He's no longer perpendicular to the far field director, right? He's a nice diagonal going across the page. Theory doesn't predict that for the weakly distorted dipole, but it does predict that the direction of the y velocity, here is 5CB, up here was flow aligning. We could expect a weak y velocity in one direction. And the flow tumbling guys that we're looking at, we should expect a change of sign. So we did see a change of sign. We saw a dramatic change of sign, much bigger than predicted. Okay, but just let's stop and situate ourselves. We know that in a Newtonian or isotropic fluid, that just the pure rotational motion of a sphere, which is an example of a very symmetric non-reciprocal motion, very symmetric, that should do nothing. And so we should have no swimming. And that in the nematic liquid crystal, it's this top view that we're looking at where the dipole goes from living on the north or south pole to being offset. That broken symmetry is allowing us to generate elastic stresses. And I guess it's really the viscous part that are contributing so much. viscous stresses associated with the misaligned nematic to drive the motion. So we should expect swimming, which of course, then the question is, what about reciprocal motion, right? So you all know the scallop theorem? Okay, so there would be nothing more frustrating than being a tiny clam. Right? Like you open and you go one way, and you close, you do exactly the same thing. So say, okay, I'm gonna try going faster. Like I'll open fast and I'll close slow. It's like, no matter what, you're screwed by fate. You're going nowhere, right? And so what happens to our guy? What happens to our guy if we wag him back and forth? Right? So we take our dipole and we tilt him and we tilt him and we tilt him and we tilt him. And will that purely reciprocal motion allow net motion? And so this is, we're going to wag this thing back and forth with a net angle of about 72 degrees of the entire sweeping. And this is what he looks like. Doesn't he make you happy? This is one of my favorite videos. So he looks like a happy puppy, doesn't he? So that's sped up a lot. Okay, so what's surviving, the way to think about it is, remember I told you that the flow field, when he was going perpendicular to the far field director, I said it was not quite, it was a very weak, y-directed part. That's all that's surviving here. That we're sweeping and we're on a weak tilt this way, we go that far that way. And then we sweep in the other direction, we go that far that way. And only the y component survives. And since it's weak, we're slow. So this is found, you can find the forces driving this just by integrating across this over a cycle. So it's quadratic in the Ericsson number in theory. What we're seeing, and this is an ongoing discussion, is something that I would argue is an onset of a flow at around order 1 Ericsson number. But Mojtaba and Steve, who are working on this, are very honest, and very careful particle tracking work is going on right now to see whether we can claim the nonlinear. Certainly you see a nice takeoff of the velocity. That it's certainly nonlinear with Ericsson number. Okay, and remember we talked about the flow tumbling motion, that we expect the flow tumbler act differently from the flow aligner. And that his y velocity, we saw, he went diagonally in the wrong direction. So here's that system. Yeah. So they're interesting fluids. So already we've established that they can generate their own broken symmetry that allow them to swim under very, very isotropic fluid forcing, and that lets them also to do this flow tumbling. Now we're taking one step closer back to the system that motivated us. So we're not going all the way back to the four-armed creature, but we're going to do something that's topologically the same. We're going to take a disc. So a circular disc out of SU8 epoxy resin, sputter it with nickel, treat it with the surfactant, and then liberate it from the base so it has this poor little SU8 face that never saw surfactant. It doesn't get to be homeotropic. And a very important feature we found out about SU8 phase, it's typically up in the movies you're going to see. We have a planar oriented boundary above it. And SU8 is often called a random planar surface. If we heat the system over the pneumatic, we have the lid in place, and then we cool it. The system, the 5CB, has a finite anchoring energy. And when it's cooled, it adopts the orientation of the lid. So we always we're starting alignment of the lid. And we maintain that orientation until we're melted again, meaning that we now are imprinted. We are our own surface with oriented planar anchoring. And if I rotate one with respect to the other, I'm going to be twisting the pneumatic. Okay. So this work is work by Claire Doré and Jackie Zhang. And Claire has led simulation and Jackie the experiments. And again, Michelle, so the height of the disk is about 30 microns. It's about 75 microns across in diameter, and the gap is roughly twice the thickness of the disk. So we're confined. We're not able to flip. So first, this is saying broken symmetries matter. If we're isotropic, nothing interesting. When we first quench, we form what we call a quadrupolar distortion. It's a weird defect. It's not like what you saw in a sphere, but symmetry, we call it quadrupolar. And when we simulate it, we think that the defect looks something like this. We have a planar face, and we have this sort of ring wrapping the colloid. Eventually, those things reorganize and become a dipolar defect that we understand a little bit better. This is the dipolar defect at equilibrium. Again, it's not a simple dipole. It's like a dipole in that at equilibrium, this thing likes to live on the north or south pole, aligned with the far field nematic. And this is our understanding of it. This is like a 500 nanometer simulation. You can't make these simulations non-dimensional because the length scale of the disclination line, the defect that emerges, you can't scale it out. Okay, so you're running these things that are very costly in dimensional form, and the scale of the simulation is about 500 nanometers. The scale of the disk is about 75 microns. So we're not married in scale. And disclination lines are really cheap if you're tiny, because you're a tiny object. It doesn't take much to wrap you. And they get more expensive the bigger you are. So we think that our dipolar defect is something like a loop hanging off on the side, but it's squeezed together. It's smaller. Okay. And usually when people do liquid crystal work, they go, yeah, no, we understood the equilibrium and just stuff like that. Okay, I'll tell you about why it haunted us as we go back and forth during the talk. This is my disk. Jackie had been doing fluorescent confocal microscopy to try to image around the disk, and we had a dye that was excluded in the region of the defect. And indeed, we got darkness where we knew the defect was, but darkness was not particularly informative about the structure. So Jackie got frustrated. He took a magnet on the stick and he tilted the disk. So here he's tilting it. Do you see like a coffee cup handle? Okay, so that's illegal in a sense that we've just perturbed them out of that space, but we can see a loop that is reminiscent of the loop that you saw in experiment. Okay, so that's where we're starting. Here's what that disk does when we rotate it. So the disclination line here is elongating. It's pinned along this edge, and then it peels off and sweeps across. Yeah, so it starts on the North Pole, elongates, sweeps across, and then contracts. Elongates. So we thought, why does it pin on that edge? Why is it pinning? And so we looked at all kinds of things. I'm sparing you data. AFM, roughness, better sputtering method. Why is it pinning? It loves that edge. We went to a disk that was all homeotropic. So this one got surfactant on all sides, and we rotate it, and it has some defect, and the defect sort of slides along, and it's a lot like the sphere. Okay. And the hybrid is faster. He's roughly twice as fast, 1.5 times as fast. So somehow the presence of that sweeping defect is storing and releasing elastic energy in some way that's driving the propulsion. And this is just to remind us this idea that the lid was planar and the SU8 took the planar signature. So as that gets twisted, as we twist the disk, we expect that in the space above the disk that we're creating some twist, right, as we go up to the top. And so we look at the swim stroke under cross polarizers. And then from untwisted there to around 90 degrees twist, there to 180 degree twist. I'll stop the movie there for a second. So for nematic liquid crystal, your nematogens, they should be the same at 180 as 0. At 0, we're black. Here at 180, we're beautifully colored. And you see that the coloration on this side is different from that side. So the twist is strange on either side of the defect. So we'll come back to that idea. We'll let the guy finish his picture, his rotation. Defect sweeps, we're at 270. And now go back to 360. And we can just go through the cycle. So clearly twist is implicated. So Claire Doré, she's actually working on 2 projects in my group. And for the other project, she's using defects to steer electromagnetic waves. And so to make sense of what she was doing, she said, you know, to get started, I have to know what I'm doing. So she programmed up the Landau de Gennes free energy functional in COMSOL. And so now she's moved over to this other project to help illuminate what's going on. And so the idea there is that there's a tensorial order parameter, which has upfront a scalar factor, which is the degree of disorder, and is weighted by the dyadic product of the vector field. And we can write our free energy functional as having 2 contributions, the bulk contribution and the surface contribution. The bulk contribution has 2 pieces, a phase free energy, which just says nematogens stay in the nematic phase, right? And so you can change the temperature in the system and melt it in the isotropic and then quench it back into the nematic phase. So it's a useful piece that we use in simulation. And then something that depends essentially on the bend, twist, and splay in the system. And so these constants L1, 2, 3, et cetera, are the energy cost to the different modes of distortion in the liquid crystal. And so free energy, we impose some preferred anchoring on a boundary of homeotropic or planar and some quadratic penalty to that orientation. And then you minimize the free energy. And as I said, it's very, very nonlinear. Different initializations, different outcomes. Okay. And again, there's the challenge that the simulation scale differs from the experimental scale. Nevertheless, it's a very useful way to learn about the topologies that emerge in simulation and do they correspond to what you're seeing in experiment. So here is Claire's result. She said, okay, she looked at constants that are like those for 5CB, that the cost for splay and bend were similar, but the cost for twist was about half that. And she took the disk and her dipolar configuration, and she rotates it. And you see the twist emerging above the disk, and then a sweeping. So in the simulation, every cycle, there are 2 sweeping events. And so in this cycle, we see that the elastic free energy, in particular, elastic free energy goes up and then goes down when we twist. When we sweep up and then down when we sweep. And you see that the twist energy up, 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 and then drops. And up, 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 and then drops. And this is great. That's what the defect's doing. It's the liquid crystal is twisting, and then this defect sweeps across and eliminates the twist. So that's happened twice per cycle. And that's not what we have in experiment. We have it once per cycle. And do you remember when I stopped us at 180 degrees? And I showed that defect that was half across the face. And neither side looked like no twist case. So this is not the answer. Okay. So then we have to, read and study. Okay. And so it works out that there are different kinds of twist defects. There's one kind of twist defect that has a singular core. And so this movie, this is an old paper in the 70s. And this is a singular core defect loop. And they were they're showing this photograph twice, several seconds apart by double exposure technique. So that was the fast video frames of its day. So there's the ring when it was bigger, and there it had shrunk. Okay. And there's a jump across the singular defect of pi. So if that was 0, it would be 180. If that was minus 90, that's 90. It's always pi. And the center is singular. And if you look at them under certain arrangements of polarizers, they always stay thin. The other defect is a non-singular defect. And so what's happening there, and I'll show you some images of it, is that the twist is escaping by rotating out into the third dimension. And it does it, it's never singular. The director field is always defined. And those appear thicker under optical microscopy, as does our defect, and they have a jump of 2 pi across. So you can imagine at my now 180-degree twist, a jump of 2 pi, well, think about it. Yeah, he's got it. Liquid crystal people always do this. They're always going like. Okay, and so we go back and we say, you know, it was very seductive thinking about the twist over top of the disk as ruling everything. But it doesn't rule everything. This is the 3-dimensional director field. And, you know, think about sticking out on the sides here. I'm going out, and then I have to twist to a line. Like with my lid, I'm going out homeotropically adjacent to the disk. And then by the time I'm at the lid, I have to be lined that way. And if I want to do it with the minimum distortion, so here I'm homeotropic, and I have to align to be aligned with the director field. Here, my shortest path to do that is rotate it clockwise. On the other side, the shortest path to do it is go counterclockwise. This thing is born with 2 different handedness. Okay. And so here's a simulation of integrating the twist angles and the rotation sense going from midplane of the disk upwards. And you see, my defect is here. Clockwise rotation on this side and counterclockwise rotation on that side. Okay, and this is a harder thing to read, but it's saying that I have rotated clockwise on this side and the same degree counterclockwise on that side. And here's just a schematic looking sort of end on at our defect. You can see the twists are concentrated in these corners, and they have the handedness that I described, going that way and right that way. Yeah. Okay. So we think this twist was already present. And furthermore, I told you that loops are cheap at small scale. So now imagine we pull those loops together. We have a thick defect, minus pi on one side, pi on the, so okay, for opposite handedness, okay. And then as we rotate the disk, as I start to rotate the disk, for example, rotating the disk counterclockwise, seen from the top of the disk is generating a clockwise twist in the Nematic. So we're starting to get the story. So first I'm going to show you just a movie where we've removed dynamics as much as possible, just to think about this idea as a twist defect instability, and then go on to look at closing the cycle and what simulation is showing. So in this experiment, what we're going to do is we're going to take the dipole and we're just going to rotate it by some angle and hold it and watch. And then increase the angle and hold it and watch. And increase the angle and hold it and watch. So I'll tell you guys, like up until you're close to 180, it's not interesting. So imagine we did that. Rotate, hold, watch, rotate, hold, watch. Okay. So we're going to take it, rotate it, hold, watch. Actually, I should be, so here's an interesting thing. Release it, let it relax. Do it again, release it, let it relax. Okay. So here, this disc has a spot on it. And Jackie said, oh, that's really nice. Now you can see how it rotates. There's never a bug that isn't a feature. Okay, so see this dot, and we're going to watch it rotate. So here we rotate this, and here we're taking it to just under its critical angle. Rotate, hold it, and release it. And this thing is pulling back, it's undoing the twist and going back to its state. So up until some critical angle, we always have a restoring elastic torque. This says go back to the way you started. And it's driven, you can see that defect is contracting as it occurs. So now, going up to a slightly larger angle. We turn off the field and it still had twist. And now it's retracting and it's untwisting. Yeah. So it's the defect's wet and it did not erase twist. It changed the handedness of the twist. And then that defect had to unwind that thing to go back to the untwisted state. So we can sketch out a cycle. We start out untwisted. We have, the cycle is going to be incomplete because you're just going to have to believe me that hiding under there is data. I could tell you anything. Okay, so we start out with no twist. And then the disk is untwisted, and under cross polars, we are completely dark, saying that we are untwisted. There's no twist over that thing. So we can say the twist over the disk is 0 degrees. Then we rotate it. As we rotate it, we're taking this clockwise domain and we're growing it over the disk, because as we do this sense of rotation, going from the top of the disk up to the plate, we're doing a clockwise rotation. So this has a clockwise sense going in the Z direction